We can also index by like distance from the right. So that would be 0, 1, 2, now 0 index because it's distant. So again, fight me or distance from the
There's an
left,
XKCD about that.
you know. Um, so wait, what happened? Oh, the 3 goes with this guy. Doesn't super matter. The point is there are different ways you could do this. We could even do some kind of like tree thing if we really wanted to. We could represent a string as like a binary tree. And that is a, we'll get back to binary trees later because they don't initially seem super clear under this scheme. But the idea is all of these things, you have a relationship. There's some kind of structure, right? Symbolic structure. And we can view all of them as having a relationship between the contents of the structure and roles in the structure. So one role scheme you might have is like exact position in the string. So we have A is in like fill. A fills 1, right? Doesn't really matter what the notation is because we're going to end in a minute. You know, A also fills role 2 and 3. B fills role 4. You know, so we have these bindings, and we can represent this entire structure in terms of some kind of binding under a role schema. So the idea is you can do this for basically any symbolic structure. You know, you make up rules like this is the left child of this upper tree or whatever, you know, something like that. Point is, this is basically sufficient to represent symbolic structures of interest as a way. So then, how can we vector that? Can we take the idea of representing a symbolic structure with contents as filler role bindings and turn that into some kind of, to use the words of the harmonic mind, connectionist representation? So the basic idea is quite simple. You have some kind of embedding for this guy. We'll say we have 3 symbols, and we'll do simple like one-hot embeddings. This is our A unit, our B unit, and our C unit. A, C. This is position roles. We have like 1, 2, 3, 4, 5, 6. So 7. I didn't even draw this number. It doesn't really matter, right? So we have whatever the roles under whatever role schema. They each get some kind of vector. So this is the vector for A. The vector could be just 1 hot, 1 hots. But the point is, what you can do with this is, well, what's an obvious way to represent A and the combination of A and 2, right? Well, one way that's very nicely unambiguous when you have orthogonal vectors like this, because all our vectors are 1 hot, so of course they're orthogonal. Just simple basis vectors is we go and we make this empty, empty, empty. 1 times 1, 1 times 0, 1 times 0, right? And then 1 times 0, 0 times 0, 0 times 0, right? We get this big whole matrix. So that's taking an outer product, right? And nice, it works. Now, if we want to represent this whole string, we can just add up all these outer products. And that's what makes a tensor product representation. A tensor product representation fill and roller bindings. Let me give a good equation that's not too much of a mess. Actually, the one in the Jupyter notebook might be. Oh shoot! Sorry, I wasn't thinking. I should have been paying attention to whether I was letting that fall asleep. If everything seems basic and redundant, it is, and it mostly will continue to be because it's linear algebra, and so everything will just work out nicely. But there are some things that maybe aren't intuitively obvious that work out. I think the notation in this notebook is a little bit less formal than.
Sorry, just.
Yeah.
So you would create one such matrix for every position in the string and then add those matrices all together, and you would end up with something where A1, A2, A3 are filled in.
Yeah.
And so on.
Yeah, it would look like, in this case, it would look like A, B, B,
right.
C.
Right.
Like that. There's 3 B's, that's why it's 7. But point is, yeah, you would end up with something like this. This is very obviously just like a concatenation of these things, but done vertically.
And then to treat that as a vector, you would just like do row-wise or
column-wise. Won't talk too much about treating things as vectors because
okay, so the native way in this formalism is to have things as matrices.
As matrices, and as we will see in a little bit, tensors as well. This is very basic. It's like a role encoding scheme that lots of people had used. Prior to this, it wasn't some new idea, but what's new is the way to analyze it. Because what's less clear is what's going to happen if you want to have, if you have distributed fillers and one-hot rolls, it's still going to be fine. It's still just going to be concatenations.
Sorry, distributed fillers.
Like vectors.
Down there. Okay. So
yeah. So like if the ABCs, those are the things that are filling your rolls, which are positions in
so if that's something other than a one-hot.
Yeah, that would be fine.
Okay.
But potentially you might have roll vectors that have more complicated structures. You might want some kind of distributed roll vector especially when your findings is something less trivial than position, or you want to have some kind of connection between, like binding between 2 objects.
Can you give an example?
So probably the best example that's going to arise will come up when I talk about trees. So we'll kind of return, I'm going to leave it unmotivated right now and return to the motivation. But the point is, sometimes you might have distributed roles and distributed embeddings, and you want to know what happens if I try to retrieve things from a representation like this, because suddenly, it's no longer just like a concatenation thing quite. It's now this matrix because you've got bits of A in all of these and bits of B in all of these. And what is the case from some also the equation in the box that's happening right there is essentially the TPR equation. We write tensor product, which is outer product, but it also does the outer product thing for tensors as circle times. And
could you make the font in the thing a bit bigger?
Yeah.
Because I can't really read that from over here.
Oh, okay. I'll write it bigger. So our tensor product T is equal. So for each filler and roll, we have a filler vector at I and a roll vector Ri. and then we sum over that for all the however many filler and roll bindings we have, and then that's in the dimensionality. So if these are in RD and these are in like what did I use? In RN. There's a reason specific to this why it's in RN, and I may come back to it if we have time. But you end up with things that are in this cross-projected vector space, right?
So D and N are just the dimensions of the original vectors.
Yeah. So nothing crazy at all. But yeah, if we're talking about another reason you might want distributed role embeddings that's maybe not clear to our use case is you might want things to be a bit confusable in the sense that you might want to have some kind of relation between various roles in a symbolic structure. You know, some of them should have some kind of connection to the other ones, and you want to pull out something. That doesn't really come up. I think that comes up more in like cognitive modeling stuff, you know, where you want to like match the mistakes that people make than you know, something where we're trying to give our thing as nice of data as we can. What we can do from linear algebra stuff is that basically, by the joys of linear algebra, there are two ways you can do what's called unbinding, which is a very trivial operation when you have fully local representations like this. You want to unbind, you want to take this representation and you want to query it for a role, right? What is in role 2? That's important to be able to figure out. There are two ways you can do this. One is with an unbinding vector, which is computed by taking the matrix of role vectors as if it was like a basis matrix, and then getting the change of basis matrix, just the inverse. You want the dual basis, and if you take, then that gives you a matrix that's all the unbinding vectors. You have the corresponding column would be, I mean, obviously in this case, right, because it's here we have just the identity matrix, and its inverse is the identity matrix. So what this tells you is because these are orthogonal, basically, the unbinding for this is going to be self-addressing. So you unbind by multiplying everything by the same thing, which you knew already from just thinking about how would I extract this column. I multiply it by exactly this vector. But that also works when you're dealing with like crazy distributed representations in both dimensions, except there's two things to consider. One is you can use self-addressing unbinding, and that's what this notebook is about. This is a project I'm working on. You can use self-addressing unbinding in any scenario, but the result when you're retrieving, so that to use self-addressing unbinding is to say, when we want to retrieve f0, so f hat 0, we take t times r0, like so. Basically, what you find by linear algebra is that this is going to be equal to the true f0 times a sum of the what we would call in this formalism analysis set of 1. Ooh, no. Oh, right. so this is if you're unbinding R0, right? So it's the intrusion of all the other roles onto this role. So they're like multiplied by the desired, by the thing that's filling it. So what's happening here is like, if the roles are really close together in space, it's gonna be annoyed with you, but if it's not, if they're orthogonal, this term is gonna go to 0, and you're going to be able to unbind exactly by self-addressing. If they're not orthogonal, it might be okay. The exact degree of okay is being quantified by this notebook. But point is, you have an exact knowledge of how much wrong self-addressing unbinding is going to be. But you can always unbind exactly as long as the vectors are linearly independent. Obviously, if you lose linear independence, this representation is just you're gonna be fully screwed because it's linear algebra.
Meaning that you won't be able to extract the information.
You'll be able to extract the ones that are linearly independent, but the ones that aren't, there's no linear algebra that will save you from that.
Right.
So what the other way to do it is, like I said, to take the column vector, or to take each of the row vectors, treat them as a basis matrix, find the dual basis by inverting it. So this is our matrix of row vectors. Row is column vectors. So this is R0, R1, dot, 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 Rn, right? If that's our matrix of those, we want to unbind each by our inverse equals the unbinding vector for role 0, unbinding vector for role 1, and you can work out by linear algebra like why that would work, I guess, but I don't think it's important super, but it does work. So starting to see why there's some point in analyzing this with distributed things. It's not necessarily that obvious why you would want distributed things, but the really important reason for this mode of analysis to exist is it gives a clear way to represent using vectors and matrices and tensors trees. How the hell can we represent trees as activation patterns? The idea is you have like an RL, and also apologies for the fact that my R's look like these. I've been told this my whole life, but and then an R, I'll make that a capital R. So this is like left child and right child type roles. So if we want to represent, and obviously you would have to extend it to do non-binary branching, but this is being made by generatives, so they like binary branching, so they don't really talk about anything. But so say we have some structure like this, where this is a tree, and it has subchildren Q and R, right? So the idea is we can represent this whole thing as a tensor product representation of the representation of the left child times actually let me turn them off. It's wrong, because if I write it wrong that would be bad. I did choose to use the same notation for a reason. And that reason is I don't want to mess this up. So the representation of S So we're building up, so we won't have the representation of this. You build from the bottom up when you're doing this. So you will have that the representation of S equals, so if this was your topmost node, you would have Q times RL plus R times, and by times I mean tensor product, R, that's how I wrote it. So we do this, and then, well, Q is a tree, so it's Q, and it has left subchildren, and so on. Well, now you just keep doing it because it's an outer product, or it's a tensor product rather than an outer product. You can just keep doing it, and it will continue to do what you expect. So you can say that we have, whatever was in there, Q times RL times whatever is in the left child of that, and so on and so forth recursively. There's you might worry about the dimensions exploding. They do if you don't have if you don't handle the fact that you can basically stick in like null roles and keep things from exploding. Like if you bind it to null, then you don't have to expanding and expanding. So as long as your trees aren't fully dense, your representation will explode. Of course, if your trees are fully dense, your representation will explode. So will your tree. That's how trees are. But the point is, you can define this recursively, and you end up with tensors instead of matrices. And why do we care about distributed things here is like, say we have a word embedding at the leaf of this tree, right? Even if we have our RL and RR as like one-hot vectors, immediately our next roll as we're going up the tree is going to be this whole representation, which works out fine, but the representation will have messiness from this guy being messy. It'll be distributed because this guy is distributed, and it'll get copied by the vector, so on and so forth. And so that it wasn't obvious to you how to, hopefully it wasn't obvious to you how to represent a binary tree in a matrix, and how you might then go about getting back what was in the tree in the matrix.
Hold on.
Yeah.
What does the dimensions of the tensor end up looking like? So the final tensor for the tree?
I mean,
how does that relate to, for example, depth of the tree, or, I mean, can just take a simple tree and show me what the dimensionality of the end result will look like.
Right. So the thing is, I haven't really worked with trees that much because I've been doing a lot of work on phonology and morphology where I haven't been using trees. And there's a smart way to do it, and if you do it the dumb way, I'm pretty sure it does blow up. But we can try and do a very simple one in any case. But
no, I mean just like that is enough.
Yeah. So what's going to happen here? So let's say these guys have dimension D. There are like lowest level fillers.
Vectors.
And then it's not gonna get into the representation of this is not going to have something weird happen yet because you're only gonna have one tensor product.
This will still be useful.
This will still be, yes, I can show you, but what it's gonna be is RD times RN. So if these guys, if RL and RR are in Rn, right? Then what this representation is just the vector for Q. So FQ times, So Q is the embedding of Q, or Q hat maybe. And then RL, Paul puts hats over everything to symbolize that it's the embedding of the thing, which is distinct from the thing.
Why does R have an L?
This is the left child. Oh, I should not call this
No,
R.
you shouldn't.
Yeah. Wait, there's P and Q in the original. That would explain why it was less dumb.
Okay.
Yes. So Q is the left subchild because the alphabet is backwards now. And P is the right subchild.
And where did RL and RR come from?
You make them. You just pick. This is a rule schema that works to make trees. It's left subchild and right subchild, and you can embed them however you want.
Okay, so those are just vectors that we came up with.
Those are vectors you come up with somehow. You could
and
maybe
those are those just general, like every left child is the same? Like the RL is the same for every left child in the tree?
Yes, because and that would be bad because like how are you going to extract it? But the trick is because we have these recursive things, the role that the other child fills is not actually RL. It fills, so say Q has left subchild P, right? Then it's P tensor product RL tensor product RL. So its role is actually.
Sorry, you're missing a symbol there.
Well, because there's no child there? Or what do you mean? Oh yeah, I'm missing, at times. Thank you. I fully did not see it. So it's the left child of the role, it's filling the role. Left child of the root is filled by Q, and that's left child. That's the role that
But
P is filling.
RL is the same RL.
Yes, it's the same RL.
Okay.
But what you're unbinding is with this stuff rather than this.
Okay.
Yeah. Now you can't use unbinding vectors. There's some matrix algebra that I'm not fully versed with, but it like unbinds nicely. Like it unbinds fine as long as you don't do something stupid. You can unbind everything.
So the end result of this is going to be a tensor that represents the whole tree.
Yes. Precisely.
Does the shape of the tensor change depending on the topology of the tree?
Like the dimension of the tensor, you mean? I don't think so. I think it works through this really complicated tree. And if that would be helpful, I can like tape it up and send it to you at some point. But yeah, it does change with the depth.
Oh, it does change with depth.
With depth, yeah.
Okay.
Yeah, bigger trees are more expensive to represent.
Okay, but for any given depth, so the dimensionality changes based only on depth, not based on like
Breadth.
breadth.
If you want to represent breadth, then you have to have.
Well, not breadth, bushiness. Like how full the
So
tree
the thing is, the way I've set it up here, yes, that is true. There's a way you can set it up to save yourself a little bit of space. In this book, he calls it pseudo trees, where you can save yourself from letting everything explode by having, when you have a completely unfilled left child really high in the tree and it's a pretty deep tree. That is relevant if you have like big fat syntax trees that are very empty. And what the rest of chapter 8 that I wasn't really planning on talking about too much does, and also I'm like not that I have to, it gets very formal, but you can actually can set it up in a kind of deterministic way, and you can unbind and bind everything and bind them back up. And he actually works through taking syntax trees of small English sentences that are in active or passive, unbinding them to figure out whether they're in active or passive, and then building up a simple like agent, patient, verb, data role scheme, like a predicate calculus representation, super simple, active, passive sentences through purely linear operations on this tensor. In a way that's kind of like Lispy, so it's a bunch of like, what's it called? Operations. I say it's Lispy because I've been told that, but I have never really used Lisp. But it's a bunch of like cons and X, like you extract, and then start to construct. You're like, do. Yeah. Yeah. And if you wanted, I could go into more detail about what is, how often do you have errors when you do self-addressing unbinding, because you're having trouble inferring something.
So an error is loss in extracting.
Error here is defined by, so assume you want to extract, it depends on how your system is set up, how you might be extracting things. So you might just extract something from the tensor product and like just use that value. But say you were trying to decode from a tensor product, so it's the output of your neural network or something, and it's bound all this stuff up, and you're trying to figure out, you're trying to unbind each, you know all your roles, you're trying to unbind from each role and find out which filler from like a set of fillers that you know is in that role. And then you want to know how often would you screw that up? How often with the fully distributed role scheme and roles picked at random? We're interested in this because we're now trying to let the neural networks learn the tensor products for interpretability purposes, because obviously this is like analyzable. But if you let them learn it, they might pick vectors that are bad. And how likely are you to screw it up? Screw it up grabbing back like your word to that vector or whatever, given that you've unbound in this way and you have this thing. So there's some intrusion here. And the answer is it scales. You know, if you don't have too many bindings relative to the dimensionality of your role vectors, it's fine. But as you approach like the ratio of those being 1, it starts getting pretty unfine, like around like 20% error or something like that.
And error means that
you unbound incorrectly. You can do that theoretically in a simple case in which, in the case of maximal intrusion, so where the filler, there's one filler in this role, and then all other roles have the same filler. You get like maximal intrusion in one direction of this term. And in that case, you can do an exact probability, and you get a very simple curve that should be somewhere here. Well, it should run pretty quick. I gotta, bam. What? slow experiments in here faster. I love Python. Yeah, so that's a example of, and it doesn't matter with the way the function is in this simple theoretical case, it doesn't matter whether you do it as a function of k and you fix n here being the dimensionality of the roll vectors, and k being the size of your symbol structure, like the number of roll vectors, the number of bindings you have, so the number of terms in your plus, in your sum. So you can vary those and you'll get the same graph. So here I fixed the dimensionality and vary the number of bound things. That way I don't have to just randomly sample larger and larger vectors in my empirical experiments. But basically you get this graph unbinding rows almost, but this actually very slightly nonlinear because this is that's like a differentiable function all the way. But yeah, it's like that's how it varies in this theoretical case, which is in theory a worst case. And in practice, it does do better when you don't have maximal intrusion in one direction and you can't do an exact estimate. And then you're trying to do it out in more practical scenarios, where you have word-to-vec embeddings and stuff, which currently our latest thing that we figured out is that if you're trying to unbind word-to-vecs in a string position system like this, it won't work out well for you if you use the Google News corpus, because there are 3 million of them, and so even if you jitter it a little tiny bit, you'll just unbind the wrong thing by random chance.
3 million. 3 million what?
3 million word-to-vec vectors.
Oh, okay.
So if you're trying to retrieve the one that's closest,
yeah,
even if you're not intruding in the wrong direction or something, you'll just randomly land on another vector because they're all almost unit length-ish. They're not huge vectors, and there's 3 million of them just clustered super densely. It's so annoying. Anything, other questions, things you'd like to know?
Yes.
Yeah. No worries.
I'm not sure what the question is, though.
Fair.
I think you and I should sit down and talk about, brainstorm about how this fits into this particular scenario.
Yeah, I would like to do that.
we could also do that together.
Yeah. We've got probably 10, 20 minutes before we need to leave for the
Plenary?
Yeah, for the talk.
Do you want to just do that now?
Yeah.
And people can jump in or not jump in as they wish. I'm going to stop videoing now. I